So far, we've been focused on the mins and maxes of continuous functions on closed intervals a, b. And that's a situation where the extreme value theorem applies. But what about other kinds of intervals? Open intervals, infinite intervals. What can we do then? We no longer have the extreme value theorem, so we're not guaranteed that the function will attain a max or a min. But the candidates for where a max or a min might be attained remain the same. We have to look at critical points, and we still have to check the endpoints. But what does it mean to check the endpoints if the endpoint is infinity, or it's an open interval and the endpoint is not in the domain of the function? We can't plug in the endpoint, but we can do the next best thing, which is to use our old friend limits. Here's an example. Let's say that f of x equals 2x squared minus x plus 8 all over x squared plus 4. And we want to find the min and the max on this interval of 1 to infinity, if it attains them. Let's actually start with the endpoints here, just so we can get a sense of the big picture. 1 is in the domain, so we can just plug that one in. F of 1 is 2 minus 1 plus 8 is 9 on top, divided by 5 on the bottom, so 1.8. And then for the other endpoint, we can't plug in infinity, so we're going to take a limit as x approaches infinity. And let me just copy this down here. All right, well, you should remember this. We can just divide the top and the bottom by x squared, and then we're going to get the limit as x approaches infinity of 2 minus 1 over x plus 8 over x squared, all over 1 plus 4 over x squared. This term goes to 0, this term goes to 0, and this term goes to 0. So we're left with the 2 and the 1, and so the limit of this quotient is just 2. Okay, let me clear some space, and then we can start drawing some of this. F of 1 we said was 1.8. So this point here is on the graph. And then the limit as x approaches infinity is 2. So we're going to have this asymptote as x goes off to the right. What happens in the middle? Well, we need to find the critical points for that. I'm going to erase this stuff down here, and then we can find f prime of x just using the quotient rule. So we need the derivative of the top, that's 4x minus 1, times the bottom, which is x squared plus 4, minus the derivative of the bottom, 2x, times the top, 2x squared minus x plus 8. And this is all over the denominator, x squared plus 4 squared. I'm going to skip the algebra, but this turns out to be x squared minus 4 over the same denominator, which is x squared plus 4 squared. And this always exists, and it equals 0 when x equals minus 2 or plus 2. Minus 2 is not in our interval, so plus 2 is the only critical point that we care about. And if we plug that in, we're going to get f of 2 equals 14 on top, and then it's over 8, and that's equal to 1.75. So up on the graph, we can put the point 2, 1.75. Okay, what does this tell us? We're beginning here at this point where x equals 1, and then the function decreases to this point at x equals 2. We haven't looked at the second derivative, so we don't know about concavity, but it's definitely decreasing the entire way. No wiggles, since we know that x equals 2 is the only critical point. And after that, we have to get up to this asymptote as x goes to infinity, so the graph is going to do something like this. And this time it's got to be increasing the entire way. And based on this, we have a complete picture of what's happening. We can see that f attains its minimum on this interval right here at x equals 2. And for max, as x goes to infinity, f is getting arbitrarily close to 2, which is bigger than it ever got before. But it never actually attains that value. So that's the sort of thing that can happen with intervals like this. And now you know how to deal with it.